In this lecture, we are going to look at a Colab notebook that does image classification using PyTorch with a convolutional neural network on the Fashion MNIST dataset. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Alright, so let's start by recognizing everything that should seem familiar. First, we have all our imports. There should be nothing unexpected here. Notice how we're also importing the datetime module. This is useful since as your data grows and your models grow, training is going to take longer and longer. When training starts to take a non-trivial amount of time, we naturally start to ask, so how long is this taking? And so we can use the datetime module to get a sense of how long each iteration of the training loop takes. In more high-level libraries like Keras, this all happens for you. But in PyTorch, if you want these features, you have to build them yourself. Next, we load in the data, which is, as we mentioned, the Fashion MNIST dataset. Since it's included in the Torch Vision library, nothing has to change in the way we load in this data. Next, we're going to check a few of the dataset's attributes to see how it compares to MNIST. Remember, it's supposed to be a drop-in replacement. As you can see, the maximum value is 255, which is what we expect. The shape of the data is 60,000 by 28 by 28, which is what we expect. And the targets contain integers that look like they're between 0 and 9 inclusive, which is also what we expect. Next, we load in the test dataset, and then we get the number of classes by casting all the targets into a set and then taking the length of that set. As expected, the dataset contains 10 classes. The next step is to define our CNN model. As promised, we're going to start looking at how to build models using inheritance rather than stacking layers together in a sequential. On the first line, you can see that the CNN class inherits from the nn.module class. This makes our class an official PyTorch module, meaning it has all the useful functions and attributes that a built-in PyTorch module has, even doing automatic differentiation. Inside the constructor, the first thing we do is call the parent class's constructor. Next, we create our layers. The first set of layers is a series of convolution layers, followed by the ReLU activation function. We can wrap this in a sequential to make it easier to call in the future. Notice that the first convolution layer has only one input channel. That's because, as you know, the MNIST and hence Fashion MNIST datasets are grayscale. As you recall, we need to do some convolutional arithmetic in order to calculate the arguments into the first linear layer. So I've left some useful links here on this topic if you want to check them out. I would recommend you do the calculation yourself to make sure that what I've written below is correct. Next, we have a series of dense layers, along with some dropouts and a ReLU activation. Again, we wrap this in a sequential, so it's easier to call later. Next, we have the forward function. This is where we actually pass a given input through the CNN to get the neural network's output. As you can see, it's made up of just 3 lines of code, thanks to our sequential objects. First, we pass our input into the convolution sequential. Next, we reshape those outputs in order to flatten them using the view function. Notice how there's no need to specify both dimensions of the flattened output. However, it may be easier to specify just the first dimension and not the second one. The first dimension simply refers to the batch size, which we can obtain by using out.size of 0. This is because if we have n samples in, we also must have n samples out. Clearly, the number of samples we pass into the input of a neural network must also be the number of predictions that we get out. The -1 means that PyTorch will automatically calculate the leftover dimension given whatever dimensions are left. Next, the third step is to pass the data through the dense layers, and finally we return the output. The next step is to instantiate the model. We pass in one argument into the constructor, which is the number of classes k. In the next block of code, I show you how to build an equivalent CNN using the sequential module instead of building a custom class. As you can see, it's much simpler, but still requires you to do convolutional arithmetic to determine the first linear layer's input size. You might want to try both models and confirm that they are equivalent. The next step is to move our model to the GPU, which you already know how to do. The next step is to create our loss and optimizer, which you already know how to do. The next step is to create our data loaders, which again, you already know how to do. The next step is to create our training function, which again, you already know how to do. The only minor difference here is that I have some timing code, and when each epoch completes, I print the duration of that epoch. So you can see here I'm printing out the epoch duration. But now you see how important it is to understand what we were doing previously. We'll be seeing that exact same code again and again. Alright, so training completed successfully at around 6 seconds per epoch. Next, we plot the loss per iteration as usual. So this appears to look good. Next, we get the train and test accuracy using the same code we saw before. As you can see, we do pretty well, about 94% on the train set and about 89% on the test set. But this is definitely less than the accuracy we got on the original MNIST dataset. Next, we have our confusion matrix code. So if we scroll down, we can see what our model is most confused by. Unfortunately, the axes are labeled with integers, so it's hard to tell what's what. But we can see if we look at the labels below, what each of them means. So it seems we often confuse 0 with 6 and 6 with 0. 0 corresponds to t-shirt and top, while 6 corresponds to shirt. So it definitely makes sense that our model would confuse these. In fact, one might argue that they are the same thing, and that even humans would confuse these. That's similar to what we saw with MNIST. We can also see that 6 gets confused with 4 a lot. As we saw, 6 means shirt, and now we can see that 4 means coat. This also makes sense, given the very low resolution of the images. Basically, they're little white blobs on a black background. We would expect that a coat has a similar shape to a shirt. We also see that 2 gets confused with 4 and 6 as well, pretty often. 2 stands for pullover, which again is pretty much a shirt, especially when it's just a 28 by 28 blob. On the other end of this, we see that 7 often gets confused with 9 and vice versa. 7 corresponds to sneaker and 9 corresponds to ankle boot. So again, considering that the images are just little blobs, this makes total sense. Let's now look at some misclassified samples to check if our reasoning holds. So the first one we see is a t-shirt top getting predicted as a shirt, which makes sense. Here's a shirt predicted as a pullover, that makes sense. Here's a shirt predicted as a coat. I wouldn't really consider that to be a coat. Here's a t-shirt predicted as a shirt. That makes sense. Here's a pullover. I think we saw this one. Here's a sandal predicted as an ankle boot. That makes sense. Here's a coat predicted as a pullover. That makes sense. So you can see that all the things that are getting misclassified are generally the same. Okay, so as a final exercise for this lecture, what you should try is mix and match the models and data that we've seen so far. Previously, we used an ANN on MNIST, and now we're using a CNN on Fashion MNIST. You should have some intuition that a CNN should perform better than an ANN, but also that Fashion MNIST is a harder classification problem than MNIST. So what will happen if you try to use an ANN on Fashion MNIST? What kind of results do you expect to see? What will happen if you try to use a CNN on MNIST? What kind of results do you expect to see? As always, remember my rule: machine learning is experimentation, not philosophy. Whenever you want to know the outcome of running some computer code, never try to guess the outcome with your mind. Well, in this case, it's okay because I've asked you to, in order to check whether your intuition is correct. But what you really want to do is write these scripts in code and see the answer for yourself.